It gives us the shapes that we have. What's the matter?
Sorry, I fell down.
Sorry, it's something. Yeah, I know I wrote behind the periodic table. That wasn't so smart. I got an email. One Direction tickets.
What?
That are going on sale. Are they on sale now or going on sale?
Yeah.
Oh, we don't want everybody to know.
No,
pre-ordered. No, we have St. Paul break here. Never mind.
I thought you brought Greg. What your name is James? All right. No, sorry, didn't mean to mess up your focus. Sorry. So I'm going to use now in Chem 1. I passed out little bits of clay and toothpicks to everybody, and we tried to go through and predict shape. We don't have time for that today. You get too distracted by the clay. So I'm going to use the clay, but efficiently.
All the Hosa people? All the Hosa people?
Then I can log in with it.
All right. Now, in order to organize the presentation of this thing, I'm going to arrange the order that we do these compounds by their coordination number. Coordination number is going to give us how many things are attached to the central atom. Those things could be other atoms, or they could be lone pairs. A lone pair also affects the shape. So that's what this number is going to describe. Bonded atoms and lone pairs. Add those two together, that's what the coordination number is. Right off the bat, I have kind of an oddball compound for you. Most of the compounds are not oddballs, but this first one is. BEF2. What makes this an oddball when we're talking about covalent bonding? Look at BE on the periodic table. Yeah. Yeah, it looks like it's an ionic compound. You've got a metal and a non-metal. That's clearly an ionic compound. However, some things that look like ionic compounds really aren't. They are covalently bonded. Fluorine, you think of fluorine as a very electronegative. It is. But beryllium does not lose electrons very well and become an ion. Because it's so small, it's got 4 protons, 4 electrons around it. It's more going to share its electrons. And the size of beryllium. Beryllium is this tiny little atom. Fluorine is this tiny little atom on the far right side of the same row. And so, yeah, these are atoms that will share their electrons, not transfer. So, what would the dot structure of this one look like? We spent a lot of time yesterday on dot structure. I'm learning about the rules for dot structure, did several examples, resonance structures. Let's go through that. You got a question, Mohammed?
This is like old, but are metals everything?
Yeah, that zigzag line over on, I'm holding this piece of clay and trying not to bend it up. This thing, everything to the left of this. Just about. Yep. How many valence electrons in beryllium?
2.
Beryllium.
2 really?
2. Right, it's on the left. Then the fluorine has 7. There's 2 of them. So we should have a structure that has 16 electrons. This thing is really going to look strange because we follow the rules that we learned yesterday about dot structures and how to do them. You were shown that when you combine the peripheral atoms with a single bond, then you go back and put lone pairs around everybody to give everybody 8 electrons. Notice that I didn't do that with the beryllium because the beryllium is not going to be able to take 8 electrons. It's one of those exceptions that it's not big enough to be able to handle 8 electrons. It's only got 4 protons in the nucleus. So I'm not going to put any lone pairs around the beryllium. The bonding electrons is it. That's all it can handle. And we need 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. We have 16 electrons. So there's nothing else to do with this. Okay? It is an exception. Yep. Now, here's something that's not an exception. The peripheral atoms, which are the ones on the outside, they always need 8 electrons. I just said it doesn't have any exceptions. What's the one exception? I get caught up in all these lies, right? Hydrogen, except for hydrogen. All the main group elements, except for hydrogen, on the outside are going to have 8 electrons. They must have 8 electrons. However, the central atom, sometimes it's not big enough to have 8. And sometimes they're big enough that they can have more than 8, like sulfur. And we'll talk about more of those too. So this is correct. And what would the shape of this molecule be? Well, Vesper theory says that the beryllium has 2 pairs of electrons on it. 2 little clouds of electrons. One's right here and one's right here. How do they arrange themselves? Do they arrange themselves in a straight line, literally?
Yeah.
Well, let's see. Here's the beryllium, the big piece of clay. Then I'll put a fluorine on the other end. Not that fluorine is smaller than beryllium. It is, I guess, but I'm just using a big piece of clay as the central atom. There's one fluorine. And if we think that these electron pairs get as far as they can from the other electron pairs, there's only 2 of them in beryllium. Then yeah. Uh-oh. Yeah, the fluorines are going to be on opposite sides of the beryllium just to get as far apart from each other as they can. What would you call the shape of this molecule? Yeah, that's a linear shape. All atoms line up in the straight line. So of course it's 180 degrees. We're going to find that with CO2, anytime, this is another example of a coordination number of 2. The truth?
Are there any exceptions to using electronegativity values to find if it's ionic or covalent? If you were to use those values to find out if something was ionic or covalent, are there any exceptions to that?
Yeah, there's exceptions too. Just like with this, I mean, I think beryllium has a real small electronegativity, and fluorine is very high, it's the highest. But it's the size matters as well. And so, yeah, that's not a hard and fast rule. Yeah.
Oh, no, I
Oh, okay.
Is there a reliable thing?
The electronegativity differences, yes.
All right.
Yes, very much so. Yes, ma'am?
The size of the clay represents the electronegativity, or like what else?
No, I'm just using the central atom as the big piece and the peripheral atoms as small. Because, this is a coordination number 2, it's obvious where everything is, but we start getting a coordination number 5 and 6, then it gets messy. In fact, I'm going to even take off these things and just look at where the 2 things are. Okay, so CO2 is like this. The coordination number of this one is 2 as well. Now, the number of bonds doesn't matter. It's how many atoms are attached to the central atom. So that only had 2 bonds. This has 4 bonds, but they still both have a coordination number of 2 because this carbon has 2 atoms attached to it, and no lone pairs them. Even though those lone pairs in the compound are not on the central atom. So this and this, they don't affect the shape of the molecule. Where if we had a lone pair on the central atom, it would. So this one also would have that shape. The carbon is double bonded now to that oxygen, the carbon is double bonded to that oxygen, but they'll still repel one another. These electron pairs get as far away from each other. So that's linear too. Anytime you have a coordination number of 2, the shape of the molecule is linear. Didn't work out, Nick? He knows you mean it, so he's playing dumb. Now we move on to coordination number of 3. This means you're going to have a central atom that will have 3 atoms and lone pairs around. So we're going to get a lot of practice with writing down structures. I don't want to just blow that part off and zip through it. Some of these at the end I'll zip through, but let's go ahead and try to do these carefully. So the hydrogen, each hydrogen has 1 electron. The carbon has 4, oxygen has 6. So that's going to mean that H2CO is going to need 12 electrons in this stuff. Who goes in the middle?
C.
Yes. Here's something. Yesterday I told you that usually the first element that's written in the compound is the central element. It can never be hydrogen, though. And all the acids, of course, start with hydrogen.
Wouldn't carbon always go in the middle? Is it
Yeah, if you have carbon, that's right. It does always go. So you've got the carbon, single to H, single to H, single to O, and then add lone pairs around everybody. You'll notice that when I do dot structures, I do the same thing every time. And I want you to do that too. Count the number of electrons. Single bonds at first. Get lone pairs around to give everybody 8. That means 8. Hydrogens don't. And then evaluate how many electrons are in there compared to how many are here. Okay?
4 more.
Okay, I'll be right there. 2, 4, 6, 8, 10, 12, 14. Oh, I need to get rid of some because I should only have 12. Brent?
Is there a loan by
Oh, well, the system that we have for writing dot structures is, we'll give everybody a single bond at first, and then we know that everybody needs 8 electrons around them. So just put double bond. You put a lone pair on everything until it has 8 electrons. So the carbon only had 6 from its bond, so I put an extra pair there, and 3 pairs around the oxygen to give it 8. But then I evaluate, okay, that has 14, the way it's written, that has 12. So now, and you would have predicted this before, we've got to get rid of some of our electrons from that structure so we make a double bond. So the carbon winds up having its lone pair erased, right? Yes, ma'am.
I remember in this PQ's class, like,
Talk loud so they can hear you.
in this PQ's class, like, we did the slanted, like, because that's not, like, that's not how you actually draw it.
Yeah, and I don't care how you draw dot structures, but you do need to be able to visualize what the actual shape is. Because you're right, it's not. It's not straight line, well, they're not 90-degree angles.
But it doesn't matter.
How do you write the dot structure? No, it doesn't at all. So yeah, I mean, is this the way that C or H2CO should look?
No.
No. Vesper theory says that the valence bonding electrons try to spread out as much as they can from each other. This could be spread out more. Yeah. So this is not going to be the correct shape of it. The correct shape is where they're as far as they can get from one another, or like that. Yeah. What is the shape of this? Nick? It is a triangle, right? And all the atoms are in the same plane. So it's trigonal planar. If you're a chemistry rookie, you see trigonal planar.
You mean trigon?
Trigonal planar. What is the angle between the bonds?
120.
Right, it's 120.
4 pi over 2.
360 degree angle. No, 360 divided by, oh.
Yeah. And I do have a model of this thing. It's up here
4 pi over
somewhere.
3.
That's radians.
Yeah, the actual.
What happened to my H2CO? HNO is there. Oh, there it is. So yeah, there's for several of these I have models of them. Now this is a little bit misleading because the oxygen should be a smaller atom than carbon. Now I don't know if they intend, because the oxygen is more electronegative and is pulling the electrons away from carbon, that it doesn't make it a bigger atom. So that's kind of shady, I guess, as I look at that. Yeah, it's not real good.
What, it's smaller?
Yes, to the right. Remember?
Oh,
As we go to the right, atoms get smaller. But it does represent the shape. The next compound that we have is HNO. This one is also going to have a coordination number 3. So this carbon had 3 atoms attached to it, giving it a coordination number of 3. For the HNO, hydrogen has 1 electron, N has, I put an N instead of 5. 5, and then oxygen has 6. So 1, 5, and 6 adds up to 12. So for this one, the N's going to be in the middle. Like that. Connect with single bonds first. Lone pairs around everybody to give them 8, except the hydrogen. Now count your number of electrons. 2, 4, 6, 8, 10, 12, 14. I've got too many electrons I need to make a double bond in this case too. So the only choice I have for a double bond is to take the N and the O and erase a lone pair from each and put a second bond between them. What is the coordination number of the N? It's 3.
3.
It's 3. The lone pair counts in the coordination number.
3.
That lone pair is definitely going to repel the bonding pairs with the other atoms. This lone pair does matter. Now, when we assign this thing a shape, the shape is not going to include the shape of the lone pair that this is making, but the lone pair does affect because it repels these other ones, so it causes them to get pushed down. It's not a linear molecule, even though I've drawn it as a linear molecule. Okay, so how should it be? So in this case, this was before H2CO. We had